Before watching this video, please subscribe this channel and click on bell icon to get the notifications for the upcoming classes.
In this session, I want to explain the Reverse Carnot Cycle for the air refrigeration. Reverse Carnot Cycle for the air refrigeration. So, Reverse Carnot Cycle is also called as a ideal refrigeration cycle. So, it is treated as an ideal refrigeration cycle. So, it gives highest performance between any given two temperatures for the any cycles. So it gives highest COP between the given temperature, any two temperatures. So the basic line diagram for the reverse Carnot cycle is the compressor. So compressor, cooler and expander, and this is the evaporator. So where the actual heat is removed, this is the refrigerator. Evaporator is also called as the refrigerator. So here the warm air from the evaporator enters into the compressor. So it is compressed, the warm air is compressed adiabatically up to certain pressure. So as the pressure increases, its temperature also increases. As the process inside the compressor is the adiabatic process. This high pressure, high temperature air enters into the cooler. So where it is cooled in Carnot cycle, the cooling process is carried at a constant temperature process. So the speciality of the Carnot cycle is the heat addition and heat rejections are carried at constant temperatures only. So that's why it gives the highest performances. So cooling process is carried at a constant temperature process. So at constant without decreasing the temperature, it removes the heat from this. It removes the heat. It's rejected. Q is rejected at high temperature. So after that, this air expands. So whenever the air expands, this temperature pressure decreases. At the same time, temperature also decreases. So here temperature is maintained constant, but here temperature is raised and pressure raised. Here both pressure and temperatures are maintained constant. Pressure is increased. Pressure once again it is increased, but temperature is maintained constant. Here pressure is increased, but temperature is constant. Here pressure is increased in the compressor and cooler also. But temperature is maintained constant here. From this, as the highest pressure, it is expanded. As the pressure decreases, its temperature so decreases. So this low pressure, low temperature air circulates inside the evaporator, that is the refrigerator. From this, the chilled air picks up the heat from the products which are placed inside the evaporator. Then it becomes warm and go to the compressor. This can be represented in PV and TS diagram. This is the PV and TS diagram. Is the first one, that is the compressor process. 1 to 2 is the adiabatic process. So PV to the power of gamma is equal to constant. This is the PV is equal to constant. This is the isothermal process. So 1 to 2. So 1 to 2 is the compressor. 2 to is the cooler. This is the here cooler heat is rejected at this is the heat is rejected at a high temperature, that is at T1. So here 3 to 4 is the expander. So this is adiabatic process, isentropic process. 4 to 1 again. 4 to 1 is the constant temperature. The temperature constant, heat is absorbed. Heat is rejected. Heat is absorbed. So at low temperature, here the specialty of the refrigerator, heat is rejected at high temperature, heat is absorbed from low temperature. So that is heat is absorbed. So as you know that the heat rejected, the area under the TS diagram is called as the heat transfer area under the TS diagram. So here for the during the heat rejected during the isothermal compression is equal to that is T1 into S2 minus, this is the T1 into S2 minus S3. So this is the S2 minus S3, this is the heat rejected. So almost this is heat rejected, but here in 4-to-1 process isothermal expansion, that is heat addition. So heat addition, so that's why this is the so total this much amount of heat is rejected, but this amount is used as a this is the refrigerating effect. This much heat is absorbed from the refrigerator, but this total heat is rejected at cooler. So this much total heat is rejected from the cooler, but this much amount of heat is absorbed from the evaporator. So you can take this heat rejected is equal to QD is equal to T1 into at high temperature T1 into S2 minus S3, that is the S2 minus S3. So heat added, that is T2 into, this is T2 into S1 minus S4. This is the refrigerating effect. So then the work done, normal formula for work done is equal heat rejected minus heat absorbed, that is Q rejected minus Q absorbed, that is T1 S2 S3 minus T2 into S1 minus S4. So now the COP, the basic formula for the COP is a refrigerating effect produced by work done. Here refrigerating effect is produced here, that is T2 into T1 S1 minus S4. So work done is equal to Q heat rejected minus heat absorbed. So you can you can submit the formula equations here T2. So here S1 minus S4, S2 minus S3, S1 minus S4. Here one thing is S1 is equal to S2, S3 is equal to S4. Then so S1 is equal to S2, that is S4. S2 minus S3, that is S2 is equal, S1 is equal to S2. So all S2 minus S4, S2 minus S3, S2 minus S4 is equal to S3. So all are S2 minus S3. Also once all you cross these S2 minus S3s, then it is T2 by T1 minus T2. The COP of the reverse Carnot cycle refrigerator is equal to T2 minus T1 minus T2. That is the lowest temperature in the cycle, lowest temperature minus difference between the temperature. This is the COP of the refrigerator for Carnot cycle. This is very important formula, that is T2 by T1 minus T2. T2 by T1 minus T2. So now we are going to solve some problems in the based on the reverse Carnot cycle. So simple problems now we are going to. So air refrigerator plant working on Carnot cycle between temperature limits. So here Carnot cycle temperature limits, that is the this is the T1, this is the T2. These whenever these limits given, you can calculate the COP directly. Here an air refrigerator plant working on Carnot cycle between the temperature limits of 30 degrees and minus 5 degrees. Here temperatures are given. By using this temperature you can calculate the COP. Okay, now it has a capacity. The refrigerator plant has a capacity of 10 tons. So 10 tons determine the power input to the plant, that is the work, that is the work for the plant. As the capacity, that is the capacity of the plant, N is given. So temperatures are given. So once by using the temperature limits, you can calculate the COP of the refrigerator, that is T1 is equal to 30 plus 273, 303, T2 is equal to minus 5 plus 273 is 268. So as it is given, the refrigerator plant have a capacity of 10 tons, so it can produce, that capacity means it can produce the refrigerating effect 10 tons, that is 10 tons, 10 into 3.5 kilojoules. So it can produce 10 into 3.5 kilojoules per second. It can remove 10 into 3.5 kilojoules per second of heat. So whenever the COP is calculated by T2 by T1 minus T2, so it is 7.657. So then the COP of the refrigerator for Carnot cycle normally N by W, that is refrigerating effect by work done. Actually it is asked to determine the power input, that is work done per second. So work done per second, that is N by, then it is work done per second is equal to N by COP, that is N is 10 into 3.5 by 7.657. This is 4.57 kilojoules per second. This is the determine the power input. The power input is kilojoules, 4 kilojoules per second or kilowatt. This is the 4.5 kilowatt. So another example for the Carnot cycle: an air refrigeration plant working on Carnot cycle requires 6.2 kilowatt. Okay, an air refrigerator plant working on a Carnot cycle requires 6.2 kilowatts. So it takes, so an air refrigerating plant working on Carnot cycle requires. So this is the work required for the an air refrigeration plant working on a Carnot cycle, 6.2 kilojoules. That is the power required for the refrigeration plant is 6.2 kilowatts. So the temperature limits, here temperature limits are given. So determine the capacity of the plant in tons of refrigeration. So here the tons of, here work required is 6.2 kilowatts. So that is T1. T1 is equal to 34 degrees. T2 is equal. So by using you can calculate T1 is equal to 34 plus 270 is 307. T2 is equal to minus 10 plus 263. Then you can calculate the COP, that is 5.97. Here so COP is equal to N by W, that is here W is given. So W is given, that is, so now refrigerating a capacity of the plant in terms of refrigerator, that is here require, here actually the problem a little bit incorrect. So plant requires to 6 point, then refrigerating capacity can produce the IC is equal to, so N is equal to W into COP. So that is so N is equal to W into COP. So W is equal to 6.2 kilowatts into COP is equal to 5.97. So this is kilowatt is equal to 6.2 kilowatt. So you can convert, it is the capacity of the plant in tons. So you can multiply kilowatt, 1 kilowatt is equal to 3.5 ton into 5.97, then it is 10.7 tons. So here this small modification you should note that. So here an air refrigerator working plant requires mean that is the work required 6.2 kilowatts. But determine the capacity of the plant. So for the refrigerating effect it can produce, that is, so W is given, so N is going to be calculated. Here that is the 10 tons.
Thank you for watching this video. Please subscribe this channel and click on bell icon to get the notifications for the upcoming classes. And share this